Welcome to this deep dive into XGBoost, a powerful and widely used machine learning algorithm. If you've wondered how top models achieve accuracy, XGBoost often plays a significant role. Before unraveling the extreme, let's understand its foundation, ensemble methods, and specifically, boosting. Ensembles combine multiple models for better predictive performance, leveraging the wisdom of crowds to reduce bias or variance. Among ensemble techniques, boosting stands out. Unlike bagging, where models are trained independently and then averaged, boosting builds models sequentially. Each new model tries to correct errors made by previous ones, focusing on data points the prior models struggled with. It gradually transforms weak learners into a strong, accurate predictor. Think of it like a team iteratively improving solutions by learning from mistakes. Decision trees are the most common weak learners in boosting, specifically shallow ones, often called regression trees or decision stumps. These simple trees alone might not be great predictors, but their ability to capture nonlinear relationships makes them ideal for iterative refinement. Each tree learns to predict a specific aspect of the target, or more precisely, residuals left by previous trees. Gradient boosting uses the concept of a gradient for optimization. Imagine finding the lowest point in a valley blindfolded. You'd take small steps, always moving downhill in the steepest direction. Gradient boosting works similarly. It iteratively adds new models that step in the direction minimizing prediction error, guided by the gradient of the loss function. At its core, gradient boosting minimizes a loss function, which quantifies prediction error. The goal of each new tree is not to directly predict the target, but to predict the of-loss function with respect to the current model's prediction. This gradient points towards the direction of steepest descent in the error landscape. Let's consider regression. In basic boosting, each new tree predicts the of the previous model. Residuals are the differences between actual values and current predictions. If our model predicts 5 for an actual 10, the residual is 5. The next tree tries to predict this residual. By continuously correcting these errors, Ensemble refines its predictions. Formally, gradient boosting builds an additive model Fm, x, equals sum m equals 1 to the power of mhm, x, where each hm, x, is a weak learner. At each stage m, we find an hm, x, that best fits the negative gradient of loss function. For a squared error loss, this negative gradient is exactly the residual. So if loss is 1 over 2 y minus f, x squared, its negative gradient is y minus f, x. The gradient boosting process begins with an initial prediction, f0, x. For regression, this is often the mean of target variable. For classification, it might be the log odds of the positive class. This initial prediction serves as the baseline, from which subsequent trees build upon and correct errors. In each iteration, we calculate pseudo-residuals. For each data point I, this is minus left, partial L, yi, f, xi, over partial f, xi, right, f, x, equals f underscore m minus 1, x, the negative gradient of loss with respect to fm minus 1, x. For squared error loss, this simplifies to yi minus fm minus 1, xi. Next, we train a new weak learner, typically a decision tree, on these pseudo-residuals. The target for this new tree is no longer original target y, but rather the pseudo-residuals. The tree learns to map input features x to these errors, effectively learning how to correct the mistakes made by the current ensemble, producing hm, x. Once the weak learner hm, x, is trained, we update our overall ensemble model. The new model fm, x, is updated by adding the prediction of the new weak learner, scaled by a learning rate nu. So fm, x, equals fm minus 1, x, plus nu times hm, x. This learning rate, a small value, controls step size and helps prevent overfitting. While powerful, traditional gradient boosting can have drawbacks. It's prone to overfitting, especially with noisy data or too many trees without proper regularization. Sequential nature of building trees also makes it computationally expensive and slow, particularly on large datasets. These limitations paved the way for optimized versions, leading us to XGBoost. XGBoost, standing for Extreme Gradient Boosting, is an optimized, distributed gradient boosting library. Developed by Tianqi, it is highly efficient, flexible, and portable. It extends principles of gradient boosting with innovative enhancements that address its shortcomings, making it exceptionally fast and accurate. It is essentially a highly engineered and regularized version of gradient boosting. One of XGBoost's most significant contributions is its robust regularization. It includes both L1 and L2 regularization terms in its objective function to prevent overfitting by penalizing complex models. Objective function minimizes loss plus a regularization term, obj equals sum I equals 1 to the power of n L, yi, hat yi, plus sum k equals 1 to the power of k omega, fk, where omega, fk, equals gamma t plus 1 over 2 lambda sum j equals 1 to the power of twj squared. Here, t is leaves, wj are leaf weights, and gamma, lambda are regularization parameters. Instead of only using first derivative of loss, XGBoost employs a second-order Taylor expansion. This means it considers both the first derivative, gi, and the second derivative, Hessian, hi. This provides a more precise approximation of the loss function, enabling faster convergence and better handling of complex loss functions. The expanded objective looks like obj to the power of t, approximately sum I equals 1 to the power of ngift, xi, plus 1 over 2 hift squared, xi, plus omega, ft. XGBoost incorporates shrinkage, which is the learning rate, and adds column subsampling. Column subsampling, inspired by random forests, randomly selects a subset of features for each tree. This further reduces overfitting and makes the algorithm more robust by preventing any single feature from dominating tree building. Both are crucial for controlling complexity and improving generalization. Another practical advantage is XGBoost's inherent ability to handle missing values. During split finding, XGBoost learns optimal direction for missing values. It automatically decides whether to send them to the left or right child node based on minimizing the loss function. This eliminates manual imputation, saving preprocessing time and often leading to better performance. While boosting is inherently sequential, XGBoost introduces parallelization during the. Specifically, it parallelizes finding best split points for each feature. Instead of scanning all possible split points sequentially for all features, it can compute the gain for different split candidates in parallel. This significantly speeds up training time, especially on large datasets. The full XGBoost objective function aims to find the leaf weights wj and tree structure that minimizes sum j equals 1 to the power of t, sum I and ij gi, wj plus 1 over 2, sum I and ij hi plus lambda, wj squared plus gamma t. By minimizing this objective, XGBoost determines the optimal tree structure and leaf predictions for each new tree, considering error reduction and regularization. This sophisticated function is key to its performance. In summary, XGBoost supercharges gradient boosting with regularization, second-order optimization, smart handling of data imperfections, and parallelization. These enhancements deliver an algorithm that is highly accurate, robust, and remarkably efficient. Its balance of performance and speed has made it a go-to choice for practitioners and a consistent winner in data science competitions. This reveals why XGBoost truly is extreme in its capabilities.